Okay, so these videos are becoming a lot more fun now that I don't battle them every step of the way. I am aware that my sound cuts out from time to time. I don't know why that is. I'm going to try to rectify it as soon as possible. I'm going to see if I can get a little lapel microphone to see if that doesn't change things, okay? I will tell you that I will speak as loudly and as clearly and enunciate as well as I can to minimize the problem in the meantime. Okay. So just know that I know that I'm trying to fix it. Okay. So let's recap where we ended last time, and it had to do again with the synthesis of acetyl-CoA from pyruvic acid. Okay. And this is the diagrammatic view. You have pyruvic acid. We end up with a decarboxylation. Like I said last time, that means that there's absolutely no more energy that can be harvested. That's what CO2 means. The tank is empty. There's nothing else that we can get out of it. What's left of it is this moiety, which is called the acetate group. That still has energy in it. But in order to continue to harvest that energy, we have to attach it to an arm called the arm of the coenzyme A. Okay. When that happens, we harvest high energy electrons in the form of NADH. And now we have this acetyl coenzyme A, which can now enter the Krebs cycle. Okay. So that's diagrammatically. What are we seeing per sugar? We're seeing the production of 2 acetyl-CoAs, the production of 2 CO2s, and the production of 2 NADHs. And as I let me remind you, here's my ATP is 0, NADH is 2, FADH is 2, and CO2 is 2. So we're keeping our accounting going. That's looking pretty good. All right, let's keep on going. Now we're going to go into the Krebs cycle. Okay, so that acetyl group has actually quite a bit of energy left in it. Okay, these are some of the reactions. You don't need to know them. I mean, it'd be nice if we don't have the time. So what we're going to look at is the big picture, and that's how much energy gets harvested at each one of these key points. Okay, so here's our Krebs cycle. Now remember, the Krebs cycle takes place in the mitochondrial matrix. So the pyruvate traversed the double plasma membrane of the mitochondria. It is now in the mitochondrial matrix, and that's where the Krebs cycle is taking place. In prokaryotes, this is taking place between the cytoplasmic membrane and the outer cell wall. Okay, at the end of the day, you need a plasma membrane in order to produce the proton gradient necessary to drive respiration. You'll see what that means in just a second. So here's the Krebs cycle. Here's the acetyl-CoA coming in. Let me make it a little bit larger so you can see it. See the acetyl-CoA, okay? What's the big picture? Well, this comes in, all right? And as we go around, various enzymatic changes take place. Here's the first one that we care about, and does a harvesting of high energy electrons in the form of NADH, and a carbon dioxide comes out. Do you see that carbon dioxide right there? Okay. And then we keep on going, we keep on going. Another NADH comes in here. See NAD come in, here's the NADH coming out. So the second NADH gets harvested and a second carbon dioxide, there it is. Okay, and as we keep on going, we notice that this step right here, as step 5, we're producing guanosine triphosphate, and that guanosine triphosphate it gets turned into adenosine triphosphate. So we actually get some ATP out of the Krebs cycle. Okay, we keep on going, and here's FAD. Here's flavin adenine dinucleotide. What does that mean? That means that we're harvesting high energy electrons again. We're getting more energy. We keep on going, and here's yet another NADH. Whew, that's a lot of energy. Okay, so let's count this. We have 1, 2, 3 NADHs in the cycle. We have 1 ATP and 1 FADH. Now remember, that's per acetyl group. Glucose makes 2 pyruvates, each one of them making an acetyl group. So in order to count for sugar, we have to take this cycle and multiply everything by 2, okay? So we're gonna go over here and we're gonna go, okay, Krebs cycle, how much ATP? Well, per cycle, it's 1, but we're gonna multiply it times 2 to get the amount of sugar. Bam. How much NADH? Well, it's supposed to be 1 here, 2 here, 3 here. That's 3 per cycle. We multiply times 2. That's 6 NADHs. That's incredible. And now we'll look at FADH. Here it is. Okay, FADH, 1 of them per cycle. Multiply times 2 per sugar. That gives us 2 per sugar. How many carbon dioxides come out? Well, it's 1, 2, and that should be no surprise. Why? Because 1, 2 carbons came in the acetyl group. Do you see that? And 1, 2 carbon dioxides come out. So the amount of carbon going in equals the amount of carbon going out. Makes logical sense. So it's 2 carbon dioxides per cycle multiplied times 2. That gives us 4 CO2s per sugar. Okay. All right. Let's keep on going here. What's the next step? Well, now is the fun part. Okay. Because this NADH and this FADH, okay, that's like chips at the casino. Those are the chips at the casino. Now we need to cash out. We're going to go to get cashed out, and we're going to turn in all this NADH and FADH, and they're going to give us ATP. They're going to give us money, okay? Because that's what ATP is. It is a currency of energy. That's the whole purpose for going through all this, okay? And as it turns out, here, let's go to the electron transport chain real quick so you guys can see what it looks like. Here's them trying to keep a counting of it. Let's see if it matches to what we've come up to, okay? So, Krebs cycle, and the Krebs cycle says 2 ATPs, that's correct. 2 molecules of FADH, that's correct. 6 molecules of NADH, that's correct. 4 molecules of CO2. Looks like what we read and what they said is the same thing, so we're doing okay. Now we're going to go into the electron transport chain, and we're going to cash out. Okay, so we have all these centers that play hot potato with the high energy NADH and FADH to create a proton gradient in the intermitochondrial membrane. Okay, so there's 2 membranes, and right between the 2 membranes, we're producing a proton gradient. Now, in case you have forgotten, protons have a positive charge, okay? If you create a gradient means that one place has a higher concentration than another place, okay? So, for example, if you put a cube of salt in water, okay, then where the cube is high gradient. Where there is no salt, that's low gradient. And physics is going to tell us that the movement is going to be diffusion of the salt from an area of high concentration to low concentration. So there's a certain pressure associated with this gradient. That pressure is many more times higher when you contemplate that is being caused by protons. Why? Because protons have a positive charge. This guy has a positive charge and this guy has a positive charge. And if you've accumulated them, they don't want to be next to each other because same charges repel. So imagine the pressure that there is inside this mitochondrial membrane for these protons to want to come out, okay? And when these protons come out, they turn this beautiful enzyme called ATP synthase. Do you see it right here? Okay. So we have protons in one side. See all these pluses? And as these protons go through this little enzyme, they turn around as if they were going out a rotation door. It turns it out. They turn it around. And as that happens, this ATP synthase inside this lollipop is turning and forcing inorganic phosphate, here I'm going to try and make it bigger, okay, so you can see it. Oop, I was going the wrong direction. I don't know why. There we go. So adenosine diphosphate and inorganic phosphate come in, and then as this thing is being turned by the pressure of that proton, it is forcing that phosphate, inorganic phosphate, on that ADP and making ATP. Yummy money right here. Okay? So how much do we make? It goes like this. As far as the ATP is concerned, well, ATP is ATP. Okay? So over here, oh, sorry, you guys aren't seeing what I'm doing. My apologies. Let's try that again. Here we go. This is what I'm looking at. Okay, that's what it looks like. So ATP is ATP. We're not going to change anything. So what we're going to do is we're going to add these. We're going to drag this all the way down to the bottom to about there. And I'm going to say plus. And I still have stuff that is not centered. There we go. And so from glycolysis, we get 2 ATP. From the Krebs cycle, we get 2 ATP. So for the whole thing, for all of respiration, we end up with 4 ATP. 4. Okay. How about NADH? Well, it's going to be, we're going to add it. I don't know, what's an easy way of doing this? What I'm trying to tell you is that when we add this, okay, this NADH in the electron transport chain, for every NADH that goes in, 3 ATPs come out. 3. So 1 NADH, 3 ATP. 10 NADH, 30 ATP. Okay. For FADH, when we do our sum there, okay, that's a little bit different. FADH has a slightly lower energy. So you don't get 3 ATP, you only get 2. That's it, okay? And now when we add our carbon dioxide, when we add that, this is not energy, but we notice that we get 6 carbons. And that makes sense because glucose has 6 carbons. So therefore we should end up with 6 carbon dioxide. So that 6 came out right. So to calculate ATP, what we're going to do is we're going to say, okay, 10 NADH times 3 ATP, that's 30. For FADH, is going to be 2 FADH times 2 ATP. That gives us 4. The CO2, we don't care. It was very cool. We found out that we had 6, but that doesn't give us energy. Now we're going to add it all across to get a total. We're going to get a total over here. And we come up with 38. Okay? So that's how much bacteria makes out of 1 sugar. 38 ATP. You and I do not. You and I make only 36 ATP. So if any of you are going to medical school and you get the question about how many ATP are produced per glucose, the correct answer is not 38, it is 36. We're off by 2. And a lot of people ask me why. And what happens is that pyruvate from glycolysis is really, really big. And then in order to make it into the mitochondrial matrix where the Krebs cycle takes place, in other words, to do this second step here, the synthesis of acetyl-CoA, it takes a lot of effort to move that pyruvate from outside of the mitochondria through not 1, but 2 plasma membranes of the mitochondria to get into the mitochondrial matrix. How much effort does it take? Enough effort that each pyruvate needs 1 ATP of energy to get the little guy in there. And then since there's 2 pyruvates per sugar, we don't use 1, but 2 ATPs. So here we subtract 2 from 38, and that's how much you and I get from every sugar, 36 ATP. But bacteria, because they don't have mitochondria, and they don't have a double plasma membrane, they have a single cytosolic membrane, they don't spend that ATP, so they actually produce 2 ATP more than we do. Incredible, huh? So there you have it. This is important because one of the questions that you have on your quiz is going to ask you how many ATPs you get per sugar from NADH. And the answer is what? We're staring at it right there, right? If they're asking how many sugars from FADH, there it is. If they were asking how many ATPs we're getting from substrate level phosphorylation, there it is. If they're asking total, there it is. Okay? So now we know all of that. Okay, we're going to take a little break here, and I'll be right back. Okay, here we are back. I want to cover a couple details about the electron transport chain. Okay, we got to see it briefly. Here's the electron transport chain. Okay, NADH and FADH are delivering their high energy electrons in order to power proton pumps and build a proton gradient that will consequently drive this beautiful ATP synthase and make ATP. Okay. One of the things I didn't cover, however, is that in order for this electron transport chain to function, once the energy in these electrons is all used up, those electrons need to go somewhere. They just can't hang around. An electron without a job is a particle of the devil. Okay, it reacts indiscriminately. So you have to have something that accepts that electron and removes it safely. And that something for you and me is oxygen. Okay, so notice on this little PowerPoint here, here's the used up electrons at the end of the electron transport chain. Okay, that means that all the kinetic energy in these electrons have been used up. They don't have any more energy, but they're there and they have to go somewhere. And where do they go? They go to oxygen. They go to oxygen. So we say that oxygen is the final electron acceptor. Okay, it also uses takes up protons, and when that oxygen receives those used up electrons and those protons, it turns into water. And this is why you and I breathe in oxygen and breathe out water vapor, because of the electron transport chain in the inner mitochondrial membrane. Okay. The oxygen is being used up as a final electron acceptor, and once it gets used up, we exhale water vapor. Okay. Now, the thing that's interesting is that we have facultative anaerobic bacteria, and we have even obligate anaerobic bacteria, which means that there's bacteria out there that can live both in the presence and absence of oxygen. And there's bacteria out there, like Clostridia, that simply cannot live in the presence of oxygen. They are obligate anaerobes, okay? They can only live in the absence of oxygen. So you might ask yourself, how is it possible for a microorganism to carry out an anaerobic respiration in the absence of oxygen? And it turns out that oxygen is not the only electron acceptor. For bacteria, there are two additional molecules or elements that will pick up electrons. One of them is nitrate, and one of them is sulfate. Okay, so when we talk about metabolism, one of the things that we're going to be talking about frequently is nitrate and sulfate reduction. Okay, so when a molecule accepts electrons and it becomes more negative, okay, that is said to be reduced. When a molecule gives off electrons and it becomes more positive, the molecule is said to be oxidized. In this instance, because these nitrates and these sulfates are the final electron acceptors in these bacteria, okay, they're being reduced by accepting these low energy electrons, and so you end up with what's called nitrate reduction or sulfate reduction. This is a very common thing that we look for in bacteria, And you're going to become accustomed to it, because in metabolism, we find it when media becomes blackened by this sulfate reduction, which causes the precipitate of an iron-containing molecule that makes the entire media turn black. Okay, so whenever you're looking at the metabolism of organisms, and you're looking for sulfate reduction, and the media goes from an amber color, yellow color, to black, then sulfur reduction has taken place, and that means that this organism is able to use sulfate as a final electron acceptor. Okay, so it's important for you to know that bacteria can use oxygen as a final electron acceptor, like you and me, but they can also use nitrate and sulfate. Okay, one last thing to tie up to finish this chapter has to do with fermentation. Okay, so here's pyruvic acid. Hopefully you remember that pyruvic acid is the end product of glycolysis. And here's two types of fermentation taking place. Here's lactic acid fermentation, and here's alcoholic fermentation. Okay, even we carry out lactic acid fermentation sometimes. Okay, when does this happen? If you have ever been sprinting so fast that your respiration cannot catch up with the energetic demands of your body, of your muscles, okay, what your cells do is they switch from respiration to anaerobic respiration. And instead of using glycolysis, the Krebs cycle, and the electron transport chain, the only thing that they end up using is glycolysis. Okay. Now this sounds counterintuitive, because as we learned earlier, glycolysis only makes a stupid 2-ATP. Do you remember that? If I bring up my little thing here, oops, grab the wrong thing. If I bring my little thing here, remember here's glycolysis, and it only makes 2-ATP. By contrast, if we're breathing, we make a total of 36 ATP. So it seems counterintuitive that our body would choose to use glycolysis. But the problem is that in respiration, you can make 36 ATP, but it takes longer to do. So if you're running away from a predator or for the bus or whatever, and you need energy now, your body switches from respiration to anaerobic glycolysis. And it says, well, I may only get 2 ATP, but at least I'm going to get it now when I need it. Okay? And so your body starts using this pyruvic acid and turning it into lactic acid. As a matter of fact, when your body hurts the next day from sprinting, what happens is that this lactic acid has crystallized in your muscles and is now shearing your muscles, and that's what causes pain. Okay? And so the reason I'm covering this is to explain why we have to undergo fermentation. Okay? And it goes back to how glycolysis works. Okay, so let's go back to glycolysis for a second. Let's take a look at that real quick at the very beginning of the lecture. Remember, here's our sugar, and then we go through the glycolytic pathway. We break it apart, and oh, look what happens here. We need NAD because we harvest high energy electrons as NADH. So if this glycolytic pathway, okay, if this glycolytic pathway is going to go from glucose all the way to pyruvic acid, it needs to make it through here, and in order to make it through here, we need NAD. If we don't have NAD, we're not going to go forward. Are you guys with me? And we're doing that in order to harvest 2 ATPs out of this thing. Okay, that's great. Now what? Well, look at the fermentation. Look at what's going on in fermentation. If we find it, what is it producing? Okay, from the pyruvic acid from glucose, here it is. It is producing what? NAD. So this is a sacrifice. This is a sacrifice. We are sacrificing high energy electrons from NADH. We're investing it investing it into pyruvic acid to produce either lactic acid or acetaldehyde. So we can produce NAD, and then that NAD can go back to the glycolytic pathway and allow us to get those 2 little ATPs. Wow, okay? So some bacteria, yogurt bacteria in ourselves, we end up making lactic acid. Yeast, they end up making alcoholic fermentation for the same reason. When you and I catch up, and we no longer have that high energy demand, and we're standing still, we have developed an oxygen debt. And so what happens is that this lactic acid slowly becomes pyruvic acid, and then that pyruvic acid goes through the synthesis of acetyl-CoA, Krebs cycle, and electron transport chain. But in order for that to happen, we need to add oxygen. So we have to stand still so that respiration can catch up with our demand, and we have to allow oxygen to come in. So this goes backwards to pyruvic acid and then go through the last steps of synthesis of acetyl-CoA, Krebs cycle, etc. And that way we can finish harvesting our last 34 ATP. Okay, so that's what fermentation is about. And that's the end of this lecture. I hope you enjoyed it. I hope you were able to understand me. Have a wonderful, wonderful afternoon, and I'll see you soon.